Sorry for those technical difficulties. So we're back. So equilibrium law. So again, it's much easier than rate law. It's completely based on the overall equation, and that makes it so much easier than having to worry about data or having to worry about a mechanism at a slow step or whatever the case may be. Really, what equilibrium law is, and the abbreviation for the equilibrium law is a capital, I'm having issues today, I guess, is a capital K is what we use for equilibrium law. Okay, that's the abbreviation for it, the variable for it. And then you notice on this one it says Kc. We're actually going to learn a bunch of different K's values. So Ka, Kb, Kc, Ksp, Kp. There's a bunch of them. We'll start by calling it just the generic Kc. And the little c is not a variable. The little c is just a notation saying that you're doing the equilibrium law based on concentrations. Okay, so little c really standing for concentration. And really the whole idea of equilibrium law is about taking at equilibrium, so you have to be at equilibrium to do this. So it's taking the concentration of the products that you have at equilibrium and placing it over the reactants concentration that you have at equilibrium. Now you might be thinking, well, don't all the reactants go away during the course of the reaction? And you know, up until now, maybe me or your other teachers, we've kind of deceived you in making you think that reactants turn into products entirely. The truth of the matter is some reactions that does happen, but a lot of reactions don't. A lot of reactions reach dynamic equilibrium at some ratio of products versus reactants, and that ratio or that relationship between the products and the reactants is expressed in the equilibrium law. And that dynamic equilibrium, once it's reached, no concentrations are going to change. So it's a kind of a fine line, and this lesson actually is going to go through a lot of figuring out where that relationship lies for a particular reaction, whether or not it does turn in completely to product, or does it stay a lot of it as reactant, or is it a half and half type thing? So we're going to get to look at all of that in this unit. So let me show you this one I wrote up here is very, very generic. Let me show you a little less generic, well, still generic, I guess. So here's a generic equation. Okay, you see we're using those small letters to represent the coefficient in front of the big letters which represent the compounds. So what our equilibrium law for this would look like would be, I'd call it Kc, okay, equals, and then it's products on top, reactants on bottom. So my first product is product C, and its coefficient is its exponent. Remember, we did not get to do that with rate law. That we did not get to actually do, and we all wanted to. Some of you tried to. So we now know that in kinetics, rate law, no coefficients in the overall balance equation are bad. But in equilibrium law, they're your best friend. So we're going to put, I'm just not having a good day with this board. All right, so D is the other product, and it gets raised to the D power. Okay, its exponent is its coefficient. And then I have reactant A raised to the A and B raised to the B. And that is my equilibrium law. And that's all I have to do. That's it. I don't have to compare rates. Can't compare rates, right? The rate's constant. I don't have to do any of that fancy stuff. I get to just plug it in based on the coefficients from the overall balance equation. So equilibrium law, again, it's a lot nicer in that, from that, point of view, from that standpoint. Okay. Now, I've kind of exaggerated the simplicity. We do have a couple of things that we have to worry about. So let's go ahead to some things to think about. In your equation, you are going to be really including in your equilibrium law only things that have concentrations. Okay, you only include in your equilibrium law things that have concentrations. And the only two phases of matter that have concentrations are aqueous and gases. Okay, those are the only two things that we are going to include in our equilibrium law, are aqueous substances and gases. See, I told you, it's just not a good day. Okay, aqueous solutions and gases. That means we are not going to include, gotta just laugh sometimes, you guys. We are not going to include liquids or solids, not in your equilibrium law. So you might be thinking, well, how do I not include it? Well, literally, you don't put it in there. Okay, so let's look at this first one. We have a gas reacting with a gas to make a gas and a liquid. So I'm going to do Kc equals, I'm putting my products on top, So it's going to be the concentration of CO2. Its coefficient's a 1, so I'll just leave it like so. And then, since this is a liquid, I am not writing it in my equilibrium law. So that's the only product I'm going to put on there. And then my reactants are both gases. So CH4 has a coefficient of a 1, and then O2 has a coefficient of a 2. And that's my equilibrium law for that reaction. I just completely ignore H2O. And again, the reason is because equilibrium law is about the concentrations of things. And if something doesn't have a concentration, then it can't be on here. The reason why liquids and solids don't have concentrations is, by definition, concentration is molarity. Molarity is moles of solute per liter of solution. If you have a pure liquid or a solid, then it doesn't possess that. Gases fall into the category of having concentration because we can compress them, or they can expand. So because they're compressible, their densities change. So because of that, they also get included, but only aqueous and gases. So let's look at number 2. We have a solid, right? We don't want to include solids, and then aqueous and aqueous. So we're going to do Kc equals products on top. So I'm going to put Ag, don't forget the charge. Okay, they're giving the net ionic equation here. You have to include the charge. And then it was to the first power, and then Cl to the first power. And then you go to put it on the bottom part, but the only reactant we have is a solid, and solids don't get included. So this right here is your equilibrium law. Okay, so again, we're using the balanced equation. We're using coefficients as exponents. We are not including liquids or solids. Okay, pretty much as simple as that. I'm not going to throw any more curveballs at you, because that really is what it comes down to. Okay. All right, let's go ahead and talk about what these values mean. Never mind. Let's do some more practice problems. Sorry, I missed those on your notes. Okay, yeah, so let's go to the practice problems and do these. So Kc is going to be equal to products over reactants. So F minus has a coefficient of 1, and then H3O plus has a concentration of 1. And then that'll be over HF is aqueous, so I can include it. It has a coefficient of 1. And then I'm not going to include H2O because it's a liquid. So that's the Kc for A. And then for B, we're going to have Kc equals products. Now look at that solid. I'm not going to even do it. This one I do need to do though. So I'm going to put H2 on top, and it will have an exponent of a 3 because of that coefficient. And then on the bottom, NH3 has a coefficient of 1, and I2 is a solid, not going to include it. So that is my equilibrium law. The equilibrium of this system is based purely on H2 and NH3. Doesn't play a part with Ni3 or I2. And we'll get into more of those logistics later. Okay, as I was saying before, let's talk about actually calculating and getting a value for Kc, because like rate law, you do come up with a value. And the value of Kc is really important. It tells us a lot about the reaction, whatever K comes out to be. So let me show you an example problem. First of all, notice they tell you you're at equilibrium. As soon as they tell you you're at equilibrium, then you're free to use Kc, because if you're at equilibrium, then that law governs what's going to be going on in this reaction. And they've told you concentrations of the O2, the SO2, and the SO3. And then they give us this reaction, and they want us to find Kc. So we're going to take and write our equation. So Kc will be the products, which is SO3, and it should be squared, over the reactants, O2 to the first power, and then SO2 to the second power. Okay. Now we have the equilibrium law. Now we can plug in to the equilibrium law because we have all the concentrations. So SO3's concentration was here, so we're going to put 0.971, and that will be squared, over O2's concentration, which was 2 times 10 to the negative 8th, and that was to the first power, and SO2's concentration, which is 3.4 times 10 to the negative 9th, and that one was squared. Please be really careful about those exponents. People forget to put them in their calculator, and then obviously you're not going to end up with the correct answer. So you might pause it, put it in your calculator, and make sure. Also realize all of this is on the bottom. Okay, so you might need to put a big parenthesis around there to make sure that it's all being divided by. So pause the video and get the answer. What you should end up with is 4.1 times 10 to the 24th is your value of Kc. Now you're probably immediately going, okay, what am I going to do for my unit? because, you know, in rate law, K's unit was really important, that little k in rate law. This is a capital K, and capital K is equilibrium law. And the great news is, well, we don't care about units in equilibrium law. There is no unit. This is your answer, okay? The reason why we don't have a unit in equilibrium law is all we care about is the size of that number. The unit on it isn't going to do anything for us. The size of this number tells us a lot about what's actually going on. And we're going to get into that here in just a second. So number matters, units don't. So don't worry about doing anything with the units. You shouldn't put a unit on equilibrium law. All right, so that's how you do that. Now, I've been saying this K is important and that it tells us things. Well, it's going to tell us about how far this reaction goes. You know, whether or not this reaction is going to produce the maximum amount of product, or is the equilibrium going to get achieved at some point and limit how much product can actually occur. So here's your parameters. If Kc is very large, so right here, and large is defined as 10 to the 10th, then that means there is more product, lot more product, than reactant, okay? For those ones, we say that those reactions have gone to completion. Now, that is the vast majority of reactions that you have ever worked with in this class, okay? You've done reactions that have gone very close to completion. The lab we did with the carbon dioxide being produced, if I had given you a little bit more time to let that continue in the introductory activity, you would have gotten to about 90 or 95% completion before it reached equilibrium. So that would have had a pretty large K value, because that reaction did end up producing way more product than some other reactions. Some reactions only happen a tiny bit. Like, for example, the dissociation of a weak acid or weak base only happens a really small percentage. So if Kc comes out to be a small number, and we define small as less than 10 to the negative 10th, then that means there's a lot more reactant than product. And by a lot, I mean a lot, a lot, a lot. And because there's so much more reactant than product, we say that that's no reaction. So if K is really big, bigger than 10 to the 10th, then that means the reaction is pretty much all product at the end. If Kc is less than 10 to the negative 10th, then that means this reaction didn't even happen. Even though you wrote it on paper, the reactants didn't produce any product. If Kc is equal to 1, then that means there's equal amounts of reactants and products. Okay, that does not happen very much. And please realize that equilibrium does not mean equal amounts of reactants and products. Equilibrium just means wherever it levels off and the rate in the forward direction is the same as the rate in the reverse direction. Okay, so Kc equal to 1 is very uncommon. However, there's still a large range that we haven't covered here. I've said bigger than 10 to the 10th. I've said less than 10 to the negative 10th. And I've talked about 1. But what about everything in between? If you look on your paper, I don't have it on your on my board, but if you look on your paper, you have that continuum there, okay? To the far right is where there's almost all product. If it gets that big, 10 to the 10th or bigger. To the far left, it's almost all reactant. But if you fall somewhere in between, like let's say you have a Kc value of 1,000. A Kc value of 1,000 means that there's more product than reactant, okay? But it's not as complete as 100% completion, okay? So there's more product than reactant, but it's not, you know, totally lopsided, okay? There's more product than reactant, but there's still some reactant left over. And again, that is very common, and it's not something we've really ever spoken about before. So if K is greater than 1, there's more product than reactant. If K is less than 1, then there's more reactant than product, okay? And you can see that on your little continuum there that you have on your notes, okay? Whether or not K is greater than 1 or less than 1 also tells us about whether or not the reaction is spontaneous or not. And you can see this on your notes as well at the top of the next page. The word spontaneous is a word that a lot of people have struggled with in the past because you can't really understand that word spontaneous until you understand equilibrium. Because the word spontaneous means that when equilibrium is achieved, so when the reaction is done changing, there's more product than reactant. Okay, that's what spontaneous means. So that would have to be a Kc greater than 1, because a Kc greater than 1 means more product than reactant. Remember, Kc is your product over your reactants. So in order for Kc to be greater than 1, this number would have to be bigger, right? When you do your little division of your ratio. So greater than 1 means spontaneous, less than 1 means non-spontaneous. So again, lots of information that this gives us. Let me show you what this looks like in the form of a problem so you can finish digesting it. So this problem says, first, which of the following reactions are at equilibrium are spontaneous? So they're asking us, they're telling us they're definitely at equilibrium, but are they spontaneous or not? So this is the whole, if K is greater than 1. So this one is spontaneous because of 49. 6 is greater than 1, so that's spontaneous. Notice I'm not even looking at the equation as we're talking about this, because that doesn't play any part for us. Now Kc of 6.8 times 10 to the negative 4th, that's less than 1. So that's non-spontaneous. And then Kc of 9.1 times 10 to the 80th, my goodness, that's a huge number. That is definitely spontaneous. I should like draw an S that's like gigantic. Okay, that's so spontaneous. There is like no product. I'm sorry, that was totally wrong. There's like no reactant left when this reaction is complete. Okay, 10 to the 80th is so far to the right on that spectrum that you have there. So that was the first question. So all we looked at were these values to determine that. The next one says list the reactions in order from the greatest extent of reaction, meaning the one that makes the most product to the lowest. So the one that we want greatest to least. So this one right here was definitely numero uno. The next biggest number will be the one that makes the next most product. So that would be A. And then the next biggest one is B, and then C. So again, those numbers give you a bunch of information, and we're going to be calculating them and using them. All right, so that's pretty much the basics of equilibrium law. Now we're going to get into something called reaction quotient, which is Q. The best way to explain this is there are going to be times when you are going to be given concentrations, and you're not going to be sure if you're at equilibrium. And you're going to need to use the idea of equilibrium to determine if you are at equilibrium. But if we're not sure we're at equilibrium, we can't use K. I mean, we can't call it K if we're not sure we're at equilibrium. So unless a problem says you are at equilibrium, like the problem we did a couple minutes ago, 2 problems we did said we are at equilibrium, then use K. Fantastic. But if you're not sure, then you're going to use what's called Q. And I don't know why they called it Q other than maybe the word quotient. They called it the reaction quotient. But I always think to myself that Q is kind of like, I'm questioning whether or not I'm at equilibrium. All right? Now the beauty of Q is that it's the exact same setup as K. We're just not going to call it K, Kc. We're going to call it Q because Q means we're not sure if we're at equilibrium. So if I was to write the equations for Q and for Kc for this equation that's here, let's do Kc first, just because you already know how to do Kc. So Kc is going to be products. Remember, we're only including gases and aqueous. All of these are gases. So SO3, and that'll be squared, over, and then we'll have O2 on bottom, and SO2 on bottom, and SO2 is squared because of the coefficient of a 2 there. So that's my Kc. You already know how to do that. Okay, now this is how easy Q is. Q equals my product, which is SO3, raised to the second power. We should get rid of this guy. Okay, over my reactants, which are O2, the first power, and then SO2 to the second power. They are exactly the same, except for this guy. One place I call it Kc, one place I call it Q. And the reason is, I'm going to use Q when I'm not sure if I'm at equilibrium. I'm going to use Kc when they say I am at equilibrium. Okay, so you can even write yourself a note, quote, at equilibrium. If that problem says that, then Kc is what you want to use. If your problem makes any reference to the fact that you're not sure if you're at equilibrium, then you want to use Q. So let me show you what this will look like. The reason why we need this is to decide if we are at equilibrium. And then if we're not at equilibrium, it'll help tell us whether or not more product needs to be made to get to equilibrium, or whether or not this reaction needs to go in the backwards direction and make more reactant to get to equilibrium, because all of those situations are definitely possible. So you're going to calculate Q, which again I'll show you this in a second, but you're going to calculate Q, And if Q equals Kc, then that tells you, oh, yep, I was at equilibrium, because Q is what it's supposed to be, and, you know, we're done. At equilibrium, hunky-dory, everything's fantastic. If Q comes out to be less than Kc, if Q is less than Kc, then that means the reaction has to go in the forward direction. Forward direction means it needs to make more product. So you're going to hear me use a lot of different terms. Sometimes I'll say forward. Sometimes I'll say it needs to go to the right, because that's to make product. Sometimes I'll say it's going to make more product. All three of those are viable ways to discuss it. We will hear all three. You can use all three interchangeably. So if Q is less than Kc, then this reaction needs to go in the forward direction, meaning make more product, meaning go to the right in order to reach equilibrium. Now if Q is greater than Kc, then it needs to go in the reverse direction. So we'll use the word reverse. It's synonymous with saying to the left, or with saying that it's going to make more reactants, okay, in order, should have a D in it, in order to reach equilibrium. And I'm going to show you how these problems work. I don't know if now might not be the best time. Yeah, let's do it with a problem so I can show you what I want to show you with this, because I really don't want you to memorize this. It's not good to memorize this, because you can understand why it is the way that it is, and I would rather you be able to do that. Okay, so let's go ahead and let me show you what this is going to look like. So the first part of this first problem, the question says determine if each of the following reactions are at equilibrium. Determine if they are at equilibrium. So we are not at equilibrium. I cannot, or I don't know if we're at equilibrium. I cannot call this K yet. I have to call it Q. And then it says after you've determined it, if it's not, figure out which direction it has to go in. So we're going to start by calling it Q, because we're not sure if we're at equilibrium. We're going to write our equilibrium law, which is HI squared, products over reactants, and H2, and then we're going to have I2, and both of those are to the first power. Okay. Now I'm going to plug in the values. These values they gave me, I'm not sure if they're at equilibrium, but I'm going to plug them in. So HI is 0.7, and that's squared. And H2 is 0.1 to the first, and I2 is 0.1. And when you take that, you plug all of that into your calculator, you get a value of 49. So Q is equal to 49. Look at what the problem told you K was. And these problems have to tell you what K is, so you can compare it. K, or Kc, same thing, is the same as Q. So that means, based on what we said before, then we are at equilibrium. Okay, no need to figure out what direction it has to go in to get to equilibrium, because it's already in equilibrium. Okay, so that's the first situation you're going to run into, is that Q is going to be equal to Kc, and you're going to be done at that point. But sometimes it doesn't work out that way. So let me show you what happens when it doesn't. All right, so again, we don't know if we're at equilibrium. We're going to call it Q. Okay, we're going to put our products, only gases and aqueous, but all of these are gases. I'm going to put the product on top. I'm squaring it because of the coefficient. Reactant on bottom. They both have an exponent of 1 because they both have a coefficient of 1. I'm going to plug in the values. So BrCl was 0.7, and that's squared. Br2 is 0.1 to the first power, and then 0.1 to the first power. That's weird. I used the same numbers, I guess. Well, makes the math really easy for us, right? Different situation, different equation. Comes out to be 49. Q is not going to always be 49. That's why I don't like that I did this. But Q can be a bazillion different things. Big, huge number, big, small number, whatever. But in this problem, Kc was 6.9. So notice those do not match. Okay, if they don't match, then your first thing is that you are not at equilibrium. Okay, so we are still in the kinetics part of this reaction. This reaction is still going on. It's either making more product to get to equilibrium, or maybe something bad happened and now it has to go back and get back by making more reactants. So this is our job to figure out what. So Kc, if you look at this, if we compare Q and Kc, Kc is less than Q. Okay, now if you had memorized this, you would say, okay, well, I looked at that paper, Mrs. Corman, and when I memorized based on what the paper said, the paper told me that it's going to go in the reverse direction. Okay, or remember we said there's lots of ways we can say it has to go to the left, You could say it needs to make more product. Any of these answers would be absolutely fine. But again, I don't want you doing it that way. I want you thinking about what needs to happen here. You know, in a really generic sense, that, grab a different color, in a really, goodness, I'm having all sorts of problems. In a really generic sense, that Kc is equal to products over reactants. Okay, so we know that the problem is that this whole value is too big right now to be equal to the Kc. We need this value to come down. The only way that this value comes down is if our reactant concentration increases. If I was to go to the right and increase how much product I had, my number would get bigger. But if I increase the denominator on a fraction, then that's going to cause this whole ratio to go down. And that's what needs to happen. Q needs to get smaller so that it can reach the value of Kc. So again, think about what's happening here. Don't just memorize and say, okay, well, it's reversed because Q's bigger. It's going to help you a lot more to think about the ratio. And if you need the ratio to go down, then the denominator needs to get bigger. If you need the ratio to go up, then the numerator needs to get bigger. So make sure you're thinking sort of in that direction so that you're not pigeonholing yourself into answers only if they make sense to what you're doing. Okay? All right. I think that is about it for now. You have some problems that you're going to work on. I will have talked to you about your assignment. So just make sure you are doing what you're supposed to be doing. If you're not understanding something, ask. If you need to rewatch the video, I highly suggest it. A lot of this lesson, a lot of this unit's lessons are going to be this way. And if you get behind, you're going to be unhappy. Okay, so please make sure that you ask questions that you need to ask. And if you need to rewatch, please rewatch either all of it or the parts of it that you need to redo. Okay.